Good afternoon, ladies and gentlemen. As Nikhil mentioned, I'm Uber's Director for Energy Storage Systems. I joined Uber in January to develop batteries for our Elevate program. Today, I want to talk to you about two things: why we're requiring an all-electric solution day one for our system, and two, how applying today's lithium-ion technology can result in a feasible aircraft. Let's talk about that first bit, the all-electric urban mobility solution from day one. We know this is an area of debate within the aircraft community. Uber had that same debate internally. And ultimately, what the team realized was that we had to think about this from a holistic system perspective rather than simply from an aircraft perspective or an infrastructure perspective. From that frame of reference, the dominant issues are system-level safety, system-level cost, public acceptance of the total system, and then system-level environmental impact. And I'll walk you through why we believe that an all-electric solution is best in each of these areas. Let's start with system safety. We need to think of the aircraft in the context of the dense urban environment in which it's going to operate. Now, in that urban environment, if there's a problem, it's going to be municipal first responders who have to deal with it. And so we have to think in those terms. Now, I know everyone has seen lots of images of burning battery packs, okay? I've spent the last 18 years working in battery safety. I've seen most of the provocative images. You can try to surprise me if you like. I've burned my fair share of battery packs, okay? I'm not going to show you any of those images today. If you want some, go look on the internet. There's lots, all right? But here's the thing that I do want to talk about. In the very short time that we've been working with lithium-ion battery packs, with the failures, with the testing that's been done, we've been able to learn how to make those battery packs fail gracefully, even under the most extreme conditions. Even in cases of fire, we're able to limit the heat release rates from the battery packs. We're able to make sure that our municipal fire services can readily control any issue with those battery packs, even in the most extreme conditions. Now, in comparison, despite 100 years of experience with liquid fuels, we still can't prevent liquid fuel tank ruptures under extreme conditions, very, very aggressive crashes, for example. And it's difficult to control liquid fuel fires that are very fast burning. Our fire and building codes reflect that reality, okay? What code officials worry about is they worry about controlling a liquid fuel fire, and they also worry about spilled or leaking fuel finding its way into a building and then finding an ignition source. So the codes respond to that by requiring secondary containment liquid fuel suppression systems on heliports, and they prohibit fueling operations on top of buildings, or generally prohibit this, on top of buildings or parking garages. So based on this issue alone, an all-electric system is really preferred. But that also brings us to our next issue, overall operating costs for the rideshare system. Remember, we're not optimizing for an individual aircraft's performance, but rather the performance of the full system. So let's go back to the liquid fuel case. This is a case where battery safety and the vehicle safety is aligned with lower cost, which doesn't happen every day. But when you think about secondary containment and foam suppression systems on a skyport, you realize that the construction costs are going to be higher for creating those kind of skyports. And not only that, but these systems require ongoing maintenance. So maintaining these systems, maintaining the skyports are also going to be more expensive if we prepare for that. On top of those added infrastructure costs, to fuel those vehicles, we'll need to schedule deadhead trips to fueling depots. And that'll reduce the operational efficiency of the aircraft overall in the system. But it gets worse. To support hybrid operations at scale, we're going to need to identify or build fueling depots and added infrastructure cost. So this picture is the fuel depot at LAX. Has a lot of available fuel. Okay, it's pretty big, but it's also a super busy airport. So even though this airport could probably handle refueling a small number of extra small aircraft, it's not sized to support a whole new infrastructure mode of transport in addition to its daily operations. Now, in comparison with an all-electric system, charging can be conducted on the skyport while the passengers are loading and unloading. So you get to do two operations at once, which is super helpful. And yes, electrification of the skyports is challenging, but the world is moving to electrification. That's a challenge we know we're going to have to face. What about other cost comparisons? Well, if you compare simply the cost of electricity with jet fuel, you could conclude that, jet fuel is cheaper. But if you consider total powertrain efficiency, you'll find that an all-electric solution uses a lot less energy per mile than a hybrid solution. And so from a system perspective, the all-electric vehicle is cheaper to operate. When we add considerations of maintenance, that tips the balance even further to all-electric vehicles. The simplicity of the all-electric powertrain, very few moving parts, means much lower maintenance cost. Just to bring that down to earth, in the last 4 years that my family's been driving a Model S, we have had zero maintenance on the battery pack. In comparison, our ICE engine vehicle, which is also great, gets an oil change every 6 months, and it's probably due for a tune-up. When we think about public acceptance of the entire system, the nice thing about the all-electric solution is that it removes two nuisance issues that we have to deal with that are related to internal combustion engines: engine noise and on-pad emissions. Now, we've made this point a lot of times, but it's so important I want to show another example. This is an overhead view of part of Tokyo, Japan. And you can see this is a huge, dense metropolitan area. There are lots of heliports on top of these buildings, but you don't see any helicopters. And what happened here is that the helicopters are now only allowed to be used for emergency operations like building evacuations because of the potential noise issues in the surrounding community concern over that. That same thing has happened in the US. In San Francisco, we have 28 heliports. One is in operation because of the noise concerns. Beyond that, in the US, even when we want to operate heliports and when the community is in support, we've run into problems where, for example, people landing helicopters on top of hospital heliports have found that the engine fumes from the diesel exhaust or from the engine exhaust get into the building's air handling system, and then the building just can't sustain that, and there's a complaint there, and that shuts down heliport operations. So that's another important issue. Okay. From the standpoint of environmental impact, we have to acknowledge that we're trying to introduce a new form of mass transportation. It would be unethical to do that without considering the impact of both the localized health effects of small engines and the broader implications of climate change, especially since we know that electric propulsion has lower impact in these areas. But even if you set aside the ethical considerations, we see cities increasingly placing limits on activities that produce smoke and CO2. In the last 2 decades, if you think about it, cities have eliminated trash burning, wood-burning fireplaces, they've instituted no-burn days, they prohibit smoking, and they've been placing limits on internal combustion engines. So this is a chart that's off of Wikipedia. You guys can download it, look at it yourself. But what it shows is when various cities and nations are planning to ban internal combustion engines. And you can see here that, Rome wants to ban internal combustion engines or of the diesel variety in 2024. And Madrid, Greece, and Mexico City are aiming for 2025. So we see that the pressure to eliminate hydrocarbon burning in transportation is just going to increase. And we can't recommend that we develop a new technology that is being phased out while we're trying to do this. Now, some people think that developing a hybrid system is a stepping stone to developing an all-electric vehicle. And if you don't look too deeply, that seems like a natural evolution. But experience in the automotive sector shows that that's not really true. What we see in the automotive sector, much like the aerospace sector, is that vehicles are designed around their power plants. Okay? And they're designed around their power plants down to the structural materials. So you don't shoehorn in a battery into a hybrid design or a hybrid into a battery all-electric design. If you examine a Model S, you'll see that it was not a derivative of a hybrid vehicle. It's designed around that all-electric power plant, and because of that, because the designers never had to contend with the mass and thermal loads of an internal combustion engine block, they were able to use different materials and structure that was better optimized for safety of the vehicle and performance. So applying a broad perspective is awesome. It gives us a target to shoot for, just like our best science fiction does. It inspires us, inspired me. These are some of the vehicles from my favorite shows growing up, and one of the books that my son has enjoyed that we've read together most nights. It's called If I Build a Car. Check it out, it's awesome. But you know, to get from science fiction to engineering fact, we have to make sure that the technology to do that is available. So let's examine whether we have that technology in place already. Now, if you're new to the battery world, you're absolutely going to question if they're going to work. My college experience predates the commercialization of lithium-ion batteries. It also predates laptops and cell phones. I am that old. I never got to take a Batteries 101 class. I suspect most people still don't get to do that. So if you go to the popular press, you're going to read about a lot of successes and failures, a lot about spectacular failures. You're going to read a lot of hype about new technologies that promise the moon and never seem to deliver. If you call a cell maker, they'll tell you what's in the spec sheet, but probably not too much more than that. And if you go into the academic literature, you're likely to quickly get lost in a lot of electrochemistry. So it's difficult to figure out what makes a good cell, what makes a bad cell, what makes a strong pack design, what makes a poor one. Okay, these things are not common knowledge. A lot of them are subtle, they're multidisciplinary, as subtle and multidisciplinary as aircraft design is. There are no simple 5-minute tutorials on this. But even though the college courses are not ubiquitous, we do have the necessary understanding in cells, battery pack design, and manufacturing to make safe and reliable aircraft. So let's talk about cell technology. Chemistries and manufacturing techniques have been improving relentlessly. If you've had a series of cell phones, you have direct experience with this. New cell chemistries promise more compelling performance. There is that gulf there between a new chemistry and actually implementing this in a mass production design. But that's something that the cell manufacturers have been doing brilliantly for the last 20 years. That advancement that you've seen in your cell phone batteries has been a lot of new innovations, a lot of new technologies that they've managed to implement in manufacturing. And then keep in mind that the chemistry tech on cells and batteries is going to get better and better. So that means that the aircraft with all electric powertrains are also going to get better and better. And it doesn't just mean that one new model of aircraft is going to be better than the previous model of aircraft. Since we're going to be using these batteries very heavily on our system, we expect them to be changed routinely. So that means that as we get better batteries, existing hardware will also get better and better. All right, so that technology is great. Can we make a feasible aircraft with today's technology? All right, yep, we can. Let me show you how. So today we'd like to announce our first cell partner for aircraft battery cells, E1 Moly Energy. Moly is an experienced developer and manufacturer of lithium-ion cells, and I've asked Paul Craig, who's their director of technology, to introduce his company during tomorrow's battery session. And I hope y'all will attend and learn more about what Moly's been doing and what they're doing now. Then we asked the team at Caram to explore vehicle design using Moly's latest high-power cylindrical cells. After that, we modeled the battery behavior in this aircraft. We were able to define a battery pack with a very modest 180 watt-hour per kilogram energy density at beginning of life, and a volumetric energy density that's comparable to a 100 kilowatt-hour pack in a Model S. Now, our ultimate target's 300 watt-hours per kilogram. That's our target, but we're talking about what we can do today, all right? And we didn't just model a brand new battery pack performance. We modeled the pack performance at our proposed aircraft operations end of life, when pack capacity would be lower and impedance of the pack would be increased. That's why you see beginning of life and end of life numbers listed. The resulting vehicle has a simulated range of 84 miles at end of life. It does more at beginning of life. Then we simulated a series of typical 25-mile flights and a 6-mile balk landing at the end of it. We assume the aircraft carries 4 people plus the pilot. I'll show you the full sequence in a minute, but for now, just to get oriented, let's look at a few cycles. We're showing the energy going in and out of the battery pack in terms of state of charge, SOC, that's the white lines. You go up during charging and down during discharge. Cell voltage, which is a much more complex curve, is shown in blue. You can see a big dip in cell voltage during vertical takeoff, another one during landing. These are high power operations. They're going to drag down the pack voltage. And then in between, you have the lower power draw of horizontal flight. Okay? In this example, we've assumed a very classic constant current, constant voltage charging to 4.2 volts. That's a very basic charging algorithm. It's not been optimized to do something faster. And we use the charge rate of 2C, which Molly believes the cell can handle under controlled conditions. Now, we set a limit that the voltage of the cell has to stay above 2.5 volts in any part of the mission, particularly during a balked landing, because that's where you run out of energy and power in the battery. Okay? So now that you're oriented, let's take a look at a full sequence of missions. What we see is that even at end of life, and this is a simulation at end of life of the battery pack, we can run 10 fast sequential trips and still maintain sufficient reserve to address a balked landing if we allow 8 minutes of charge time between those missions. Okay? After those 10 trips, we need a longer recharge time to continue. If we increase the charge time to 9 minutes, we can keep running the aircraft at this mission density without limit because the energy in and out are balanced for these mission segments. Now, do we want to improve cell technology? Of course, and we have a plan to do that. I'll talk about that another time. Now, is the battery pack design going to be challenging? Yes, of course it is. If you look at modern EV battery packs, you can see the design has progressed really far from a rudimentary laptop pack where you connect a bunch of cells together, put a simple BMS on it, and call it good. Now, state-of-the-art designs mitigate a wide range of possible failure and reliability and safety issues. Things like latent defects, spontaneous thermal runaway reactions, short circuit, unexpected cell degradation. As an example, these are some recently published photos about the Model 3 battery pack. They appear on Motor Trend's website. Now, you can see this is a pretty complex assembly. There is a lot of tech. There is a lot of stuff going on here. If you want to have some fun, come find me later. If you can tell me why that stuff between the cells is teal-colored, I'll buy you a drink. All right. To adapt these technologies to building we're going to do aircraft. We're building a team of experienced folks who have designed, tested, validated, and manufactured state-of-the-art, high-quality battery packs. We intend to use that expertise to design a pack and then to identify a manufacturing partner that can build these batteries to our specifications. Is this going to be easy? No, it's not going to be easy. Is it going to be impossible? No, it's not going to be impossible. Is it going to be magic? No, it's not going to be magic. It's going to be diligent engineering. And we know that with diligent engineering, we can make cells and battery packs for an economically viable solution. And since the technology is going to continue to advance, we're not going to stop at economically viable. We're going to keep moving to more and more awesome. So thanks very much.